Limited by power. Access to power is changing the industry's view about energy efficiency, which impact all levels of the system stack and abstractions. AI is seen as a massive computation problem, but that's not the case, at least with the way that the problem is structured today. It's a data movement problem. This not only limits performance but presents most of the energy consumption. In addition, the industry spends most of its time and effort to making small improvements that optimize aspect of the existing architecture, when what is really requires are major changes to the way the problem is addressed. That's not the card today. The industry is starting to face new problems such as availability of power because consumption is vastly outstripping the rate at which new power can be brought online. The sheer computational demands of the modern applications, from generative AI like GPT-5 to hyperscale cloud services requiring tens to hundreds of thousands of GPUs, have pushed the industry into critical power crisis, says Noam Prasad, VP Solutions Engineering at Protein Techs. Global data center electricity consumption is climbing sharply and projected to exceed 1,000 terawatt hours per year by 2030. Additional power is getting scarce. If you wanna get a megawatt of extra power in a week times, this is extremely challenging, said Barandinath, commander, fellow at Cadence. Then there are the operational costs, which are defined by the power utilization of the system. Hyperscalers have become extremely focused on optimizing the power efficiency of their systems, all the way from the chips to the system level. That feeds into the CapEx investment, the CapEx OpEx cost, and their profitability. So it's becoming foremost in the minds of everybody working in this industry. AI is also seen as something new, when in fact the most of it's built upon 20 years old technology. We see a lot of power wasted using classical computer architectures, said Andy Heinig, department head of the efficient electronics of Fraunhofer TUS Engineering of Adaptive System Division. To get the new architectures, you needed basic research from the universities. The new architectures are only possible with the new generation of engineers. They have a total new mindset and are trained from the beginning in those new architectures. If you train them with these existing ones, you get stuck on that. First-class citizen. Traditionally, power was the afterthought. The first industry to take care seriously was mobile phones, when battery life became a selling point, oftentimes eclipsing the functionality. This drove the development of many tools and techniques to reduce power consumption. Those solutions have now started to migrate into other sectors. There are two aspects to it, said Suhail Saif, Director of Product Management at Solutions Engineering at Keysight. One is technology readiness and the second is technology adoption. From the EDA side, from the design processes side, the technology is there. Within the mobile industry, they have the expertise. They are doing what is needed to take care of power consumption, power savings, and power optimization because battery life was king. For industries that had a reliable source of power, it was not cost effective to spend the time on power reduction, so long as it remained within the reasonable envelope. Today, not only is power become a precious resource, but power consumption ends up being a thermal problem, which is also becoming a limiter. If we look at the client platform, power is first-class citizens. Set cadence, commander. We have to think about power from day one. If you look at what's happening with the AI build-out, two things are extremely critical. The AI build-out will not be limited by availability of compute power, but more by access to power. If you look at the projections through to 2030, they predict that AI will represent about 12% of the total power consumption in the US. You really need to make sure you can build out the most efficient compute, both from a performance and power perspective. Given the power limited capacity you have in the industry. Even in those cases, it's not clear that power is as important as performance. Power is a soft limit, said Marcus Sweeney, Director of Product Marketing at Ansys, now part of Synopsys. How much power can you afford? The thing you can afford more power dissipation as long as you're willing to pay the price for cooling it. It's really an economy trade-off, and more power typically means more speed. Today, the computational demands and the competition with the AI places a premium on performance. They want the fastest chips, and if that means spending several thousand more than heat sinks and fans, so be it. Once performance demands plateau, then people will say that we can't afford to have this much power. The industry has a tendency to play it safe with margins. Semiconductor companies are paying for the same problems twice, wasted power and throttled performance, set protein textures broadside. Fixed voltage guard bands were meant to provide safety, but more time they have become an energy tax baked into every chips. Guard bands assume that every worst case will happen at the same time. In reality, that almost never occurs. Yet the chip is forced to run at this inflated voltage all the time. The result is simple. The chip burns energy it does not need to use. It's possible that the industry is sitting on a cusp. I want companies to start looking at power as a first-class citizen. Set it aside safe. This used to be the conversation 3 years ago, but with everything that is changing, with AI chips and power envelopes being dominant factors controlling or deciding will you be able to do something or not. The front runners have brought the amount of culture change in terms of considering power to be primary metric of design. So it's cultural change. It's a change about how you are thinking about what will make or break your trip. They made personal changes. They have made processes changes. Some of those changes can quick reward. extra voltage creates an extra heat that blows third. The extra heat forces the thermal protections to kick in. Those protections reduce the frequency. The chip slows itself down to survive. The silicon is capable of more, but it cannot deliver it because it was overvolted in the first place. The safety margin was supposed to protect the performance and end up limiting it instead. This is a complex problem the industry may not be ready to adequately address. When you go to the back to the design process, you can optimize in that, said Commander. It varies from design to design and is what in the 10% of 20% range. However, the biggest leverage comes from exploring different architecture for optimal meeting the power and performance targets. Some designs, especially in the DSP data path-centric domain, have used high-level synthesis to quickly explore different architectural configurations before they commit to a particular architecture. This requires a different skill set. RT used to be considered the most shift left you could do, set aside. But today, the power planning and budgeting the start in the architecture step. I see companies that have architecture power performance teams and they are mostly heavily focused on power rather than the performance. It used to be the other way around. Those teams are also becoming larger than ones focusing on backend power optimization. While backend tools and methodologies may be in place, system-level ones are not. RTL estimators are fairly accurate, said the commander, with a little bit of tuning. They can come within 10% of implementation, but you have to spend a fair bit of time and effort to tune the RTL-based estimations to backend implementation. The problem is that higher levels do not have all the implementation details. For example, what is your clock structure? To get this level of details implementation knowledge into front-end space is difficult. What you are trying to do in front-end estimation is to explore different implementation options earlier on, so that you have a relative ranking of the different implementation schemes. You fix the microarchitecture to meet the power targets. An architectural problem. The energy savings requires a not in the 10% range. To get larger gain, you have to move up in the system. You have to move up in abstraction. Fully instrumented hardware that can provide power performance feedback to the software developers allows learning and development of the best practices, said Stephen Wu, fellow and distinguished inventor at Rambus. This may include creating mapping algorithms to hardware and better understanding the trade-offs between the memory tiering, data storage and retrieval, and recomputation. Using smaller data types where possible, such as FP4, converses bandwidth with reduced data movement power. Power delivery itself is also changing as the industry transitioning to the higher voltage like 84 volt for more efficient power distribution, converting down from the 48 volt to semiconductor component levels like 5 volt and 1 volt should be done near the component themselves to further reduce more power losses. Now, part of the entire system should escape a keen focus on power. If you look at the next generation data centers, you will find racks where each rack consumed 800 kilowatt, said David Kuo, Vice President of the Product Marketing and Business Development at Point2 Tech. There is a lot of effort to reduce that. You have to start looking at it. not at the chip level, but at the rack scale level, or even the data center level. It's not about the transistor anymore. A major part of the power consumption is moving tasks, moving data, and just moving bits from one location to another. And that's the interconnect itself. The interconnect and the data passing across, it is a big part of the problem. On increasing the share of the power budget is consumed in the movement of data, and both between the processors and memory and between processors, said Rambus Wu. Computer architecture needs to keep the data as close as possible to where the processing occurs. This will mean larger superchips composed of multiple reticle-sized die co-packaging together into a one larger processor with amounts of directly connected memory to support them. The emergence of the more specialized chips and cores targeted at specific high-level functions will also improve the performance and power efficiency. As the compute problem grows in scale, so do the racks. The entire system needs to work together, say point to take cool. The interconnect portion within the rack can consume anywhere between 10% to 15% of the total rack power consumption. How much can we reduce the energy consumed by the interconnect? Take that energy and give it back to the compute portion. Another aspect of the problem is that the software algorithm they're moving so fast that the hardware architectures have to remain flexible enough to handle changing workloads. Depending on the application, we've seen the proper data preprocessing can heavily reduce the size of an otherwise power-hungry neural network, said Benjamin Prouchy, Group Manager for Advanced Mixed Signal Automation at Fraunhofer TÜV IIS. However, this investigation takes extra development time and might be limited to a specific application. Thus, the cost of power will often be externalized to the user instead of being considered in the design phase. Only when seen a benefit of the user and included as part of the product requirement will the extra time and effort to be spent on design to reduce power. Flexible architectures go against the trend for domain-specific computing, which can focus on power reduction for precisely defined workloads. The requirement from our customer is to define IP for the target performance within a very efficient powering cost envelope, said Commander. The vendor designed both hard IPs and software IPs, and now going into the chiplet space, we have to design for power all the way from the front end of the flow to the back end of the flow. Typically, a lot of these IPs are targeted for certain applications which are associated with a critical workload. We really have to make sure that we work very closely with microarchitecture and architecture teams to get the workload of interest. We have to optimize it all the way through the synthesis and place and route and basically the sign-off flows to make sure they meet optimal power envelopes. Analysis. There is still room for improvement at the back end, where new sources and energy waste are being eliminated. The frontier is that glitch power which has long been neglected, said Ansis Swinen. Glitch power is a significant portion of total power, but since it's not even part of the logic, it shouldn't even be there. There are various kinds of glitch power, and it's been tough to modify the design to reduce it. It all depends on the precise timing of the signals. It's only recently that tools have existed that are able to analyze this early on and reduce it, identify the top contributor and fix those. While workloads can be used to examine power at the block level, it becomes more difficult as the system size grows. Emulation is a stopgap solution at best. Set safe. It does enables you to look at the working scenario of the chip and test whether it will stay in power budget and if it will hold its thermal limit. It does enable you to see if the power delivery network will be able to successfully deliver the power or fail in some cases. Emulation enables this, but it is also expensive and time-consuming to get the necessary RTL. When we be back to this topic of needing a system level solution without the need of emulation, where you define the inputs and outputs of the system, the expected functionality of it, and then the solution would be able to give you the realistic way of exercising the real-world scenario. It's becoming critical to look at the workload of interest when optimizing the design. There is a growing need to run larger and larger vectors, typical emulation platform, said Commander. When you look at the design with a given workload of interest, opposite set of the workloads with some weight vectors based on the design context, you can actually drive this optimization, placement optimization to drive the high activity nets closer together. This reduces the capacitor impact on the interconnect, and you go through the clock tree synthesis and routing to optimize design. That is typical how design optimization will flow. To bring this kind of analysis up to the system level requires new tools, new models, and standards. There needs to be an industry-wide effort to set aside. There are a few IEEE initiatives, one of which is UPTC, the Universal Power and Thermal Coalition. The major players are taking part of that and bring to the light their own in-house solution. Together, there is a discussion about how those solutions could help shape universally accepted format that would work for the most companies. Most designs, it is really challenging to create something that would work for everyone, but even something that would work for most situations would be accepted by those participants. It would not only need the consensus from these major players, but it would also need investment commitment from major EDA. Much of the work is currently being done with the system companies. People are running blind, said Ed Seth. All the big houses have their own in-house, homegrown, custom solutions that work for their system design. For their architectures, software microarchitecture, and its interaction with the hardware, they have some way of estimation power and performance at the stage. The moment you try to scale them or apply them to different problems, they fail miserably. There is a hole in the EDA space for a reliable, universally accepted solution. Conclusion: power has risen in importance because today it has impacted the bottom line of the hyperscalers as a direct cost to building data centers and running them, both in terms of energy consumed and the cost of cooling them. It is creating the problems associated with the availability of the power because the generation industry cannot keep up. Power has a highly visible cost. The industry lacks the tools, methodologies, and architecture necessary to make a meaningful impact in the short term. Editor note: a second part of this story will examine both the emerging technology that may have a significant impact on the reducing energy consumption and the technologies that holding the industry back. Today I read this article, The Limited by Power. Thank you for your time. See you next time.